All right, we're continuing with Chapter 1 in the geometry textbook. In this video, we're going to go through Section 1.4, which is on angles and their relationships. All right, so up to this point, we have talked about angles, and we've actually talked a good bit about the meaning of angles informally. But now, in this section, we're going to be given an official definition of an angle. So, okay, this section introduces you to the language of angles. So these are more official mathematical definitions for angles. Recall from section 1.1 and 1.3 that the word union means that two sets or figures are joined. Yeah, so union is just if you have a set A and a set B, it's everything in A and everything in B. That's A union B. All right, so here's the official definition of an angle. An angle is the union of two rays that share a common endpoint. So an angle is the union of two rays that share a common endpoint. And let's see, the preceding definition is illustrated in figure 1.46, in which ray BA and BC have the common endpoint B. So yeah, here's an illustration of that. All right, so let's think about exactly what the official definition of an angle is saying and how that compares to what we talked about regarding angles informally. So, okay, we can start off with, we've got two rays. So, all right, there's a ray, there's a ray. So, A, B, C, D. We've got ray, here we've got ray AB and ray CD. There's two rays. Okay, so what else? It's the union of two rays. All right, so we could say ray AB union with CD. That would be this entire ray plus this entire ray. Okay, is that it? But they need to share a common endpoint. Okay, so we need to do this. All right. Now we've applied all of the constraints of the definition. So here we've got ray AB and ray AC, and they're in union. The union, they're not in union, the union of that, so all of this taken together is an angle, okay? And so, you know, that makes sense. There's an angle, right? When we think about informally how we talked about angles, this has all the requirements. We've got two straight sides and we've got a vertex. And there's an opening, but a rotational opening, a rotation by the vertex between the two straight sides, but that's not a requirement because if they were on top of one another, that would be an angle of 0. But yeah, kind of. I mean, you need an opening, but technically by the definition, no opening means 0 angle, 0 degree or whatever angle. Okay, so you can think about it when if you see the union of two rays, but the first letter isn't the same letter, then that's not going to be an angle. You need it's not. So this wouldn't work. If you had ray AB in union with ray CB, that's not an angle because the second letters are in common, but the first letter specifies the endpoint of the ray. It doesn't matter if these 2 points were the same letter. That doesn't mean anything. It's that so this is not an angle. It's you can think about, you need to have the union of two rays that have the first point is the same, the second points don't matter. I mean, the second points couldn't be this. Well, they kind of don't. You couldn't have, yeah. Well, you couldn't have the first letter match up and the second letters also match up because then it'd be the same ray. You wouldn't do that. You can't. I can't put a B here because then that's suggesting it's the same ray. Then I have to draw it on top of one another. So the second letter is going to need to be different. The first letters need to be the same, and you're taking the union of those two rays. That's an angle. So that is the technical, mathematical definition of an angle. Now let's compare that to how we looked at angles informally, how we looked at angles informally in previous videos. Okay, and I personally like the informal definition because I'm coming from the perspective of a non-math major, like an engineer, but you can, or not just engineer, anything that's non-math made, just applied math. But you can think about these official definitions are going to be important for proofs and theorems etc., which we're going to read through all that, but we're not going to be learning how to do math proofs. We'll read through it. Okay, but from a mathematician's perspective, the official definitions can be important, really important. From an applied math perspective, not as much. And really the informal definitions are a lot more helpful, because if all you remembered was the formal definition for an angle, then you might look at something like this and say, okay, we've got these two line segments here. Well, first of all, these aren't even rays. But even if they were rays, let's say, well, yeah, I can make them a ray. Why not? So ray AB and ray CD. Okay. Well, the union of ray AB and CD here, that's not an angle. If I said the ray AB in union with CD, well, there's no vertex there. For an angle, you have to have a vertex. You have straight sides and a vertex. That's the key. That's the two requirements. Technically, there's no vertex here. But it's informally, though, you look at it like you can take we have two straight sides here. So there we've met that requirement for an angle. But then even if they're segments, whatever they are, you extend them hypothetically in all directions, and for one of those directions, there should be an intersection, and that's like a virtual vertex. But I'm making this word up, virtual vertex. That's not an official math definition, but that's kind of the idea. And there you would define, okay, this would be point P, and now the union of PA, ray PA and PC, that's an angle, but that angle there, that is the angle between these two lines here. Okay, and so that's probably how mathematicians would do it. If they had just a segment A, B, and C, D, then to define the angle, you would call this point P. But I'm just saying, the informal descriptions can be just as powerful as the formal definitions. And the formal definitions from a non-math major can be confusing. Non-math major perspective can be confusing. Just be aware of that. I'm sure the mathematicians have a nice, efficient way of describing with a precise, definitive definition of angle, an angle between two segments like this, but still, it can be confusing. Okay, but then at the same time, you get into skew lines, and in the previous video we talked about the angles between skew lines, but that can be confusing from the perspective of the official definition of angle as well. However, it's absolutely logical to think about the potential of there being an angle between two skew lines. Absolutely. So, again, it's just you want to distinguish between an official math definition and the more informal descriptions we make that are still very powerful to describe that feature of geometry or whatever. Okay. As shown, the angle is represented by angle ABC or angle CBA. Yeah, in that figure, I'll bring that figure in. Okay, so the angle, you can say angle ABC or angle CBA. The rays BA and BC are known as the sides of the angle. The angle B, the common endpoint of these rays. Okay, so there's figure 1.46. So as shown, this angle is represented by angle ABC or angle CBA. The rays BA and BC are known as the sides of the angle. B, the common endpoint of these rays, is known as the vertex of the angle. When three letters are used to name an angle, the vertex is always named in the middle. Recall that a single letter or numeral may be used to name the angle. The angle in figure 1.46 may be described as angle B. The vertex of the angle is angle 1 or as angle 1. In set notation, we see that angle B is equal to the union of ray BA and BC. So you can say angle B, angle 1, angle ABC, angle CBA. And again, this is the union of ray BA and BC, with that first letter telling you that the rays share a common endpoint. All right. Postulate, the protractor postulate, the measure of an angle is a unique positive number. Yeah, that makes sense. That's like saying that a length is a unique positive number, the length of something. And it's unique in the sense that what they're saying there is if you have something in your hand like a piece of metal and it has, you think about its length or one of its dimensions, that's one, it has one and only one actual true length. One. Now, someone may measure it and get one number and you get a slightly different number, but that's just like measurement uncertainty. Technically, there's a length of something, any length measurement, the actual true measurement is one positive number. It's not multiple. You can't something can't be two different lengths at the same time. It's the same idea with an angle, right? It's exact same. You would think it's the exact same logic applies to an angle. Okay, note in chapters 1 to 10, the measures of most angles will be between 0 degrees and 180 degrees, including 180 degrees. Angles with measures between 180 and 360 are introduced in this section. These angles are not often encountered in our study of geometry. Yeah, we talked about this before. Most protractors go from just 0 to 180, but you could just play with the orientation of the protractor, and it's easy to use a 180 degree protractor to get an angle between 180 and 360 if you need it. There's also 360 degree protractors as well. So, but yeah, in general, an angle is a full rotation. So angles are going to be, in terms of degrees, they go from 0 all the way to 360. Something between 0 and 360, you could have any angle like that is valid. But like if you've got something that's oriented kind of upside down, then maybe you'd rather just describe it as just between 0 and 180 and just specify what the orientation is. So it's kind of personal preference. You don't have to use you don't have to use something between 180 and 360 if you don't want to. You would just say, look, I'm measuring the angle looking down at it. Or you could make it, you could design the system to where, look, every measurement is taken if you're standing the thing straight up and down, and you're standing straight up and down, no matter what. In that case, you use the full range, 0 to 360. Types of angles. An angle whose measure is less than 90 degrees is an acute angle. If the angle's measure is exactly 90, the angle is a right angle. If the angle's measure is between 90 and 180, the angle is obtuse. An angle whose measure is exactly 180 is a straight angle. Alternatively, a straight angle is one whose sides form opposite rays or a straight line. A reflex angle is one whose measure is between 180 and 360. So you might not be, I think most of us are pretty familiar with all the terms except for reflex angle. That's pretty interesting. You could catch someone with a question, well, what's an angle called between, you have acute angles, obtuse angles. What about an angle between 180 and 360? What's that called? Is that obtuse? They say yes and say no, it's a reflex angle. Okay, but you also have right angles and straight angles. Straight angles are 180 degrees. It's two rays that are going in the opposite direction. In figure 1.47, angle ABC contains the non-collinear points A, B, and C. So let's see. A, B, C, non-collinear points. Unless otherwise stated or indicated by an arc, angle ABC is an acute angle. Oh, okay. So what are they saying? What are they talking about here? What they're saying is that if you've got three non-collinear points in a plane, okay, well, I could look at this, between any 2 points you form a straight line. So this defines two sides, right? And I'll make them two rays. But they don't have to be rays. You can think about this in general for any angle you're analyzing. Okay, so when you see this, what you can think about is that there's two ways you could look at this. You could say, okay, yeah, look, it's this common endpoint here. There's an angle here, all right. But why not this? This is also an angle. So which one is it? What they're saying is that it's always going to be default that you assume the acute angle, unless it's otherwise made clear that it's not the acute angle. Okay, so here we've got all the requirements for an angle here. We've got two straight sides and a vertex. Okay, but there's two potential angles. You have this angle, or you have this angle? Well, it's not otherwise indicated, so that means we're referring to, if we're looking at this as an angle, it's talking about that angle, the acute angle. All right. The 3 points A, B, and C also determine a plane. The plane containing angle ABC is separated into 3 subsets by the angle. Well, okay, let's come back to this statement here. The 3 points A, B, and C also determine a plane. So, yeah, we've talked about in previous videos that if you have 3 non-collinear points, that determines a plane, right? Well, another thing we can think about now is that if you have 3 non-collinear points, then that sets an angle as well. Once you have 3 non-collinear points, that also it constrains an angle as well, because you have 2 lines. If you have 2 intersecting lines, in the previous video, I think it was the previous video or 2 videos ago, 2 intersecting lines, that means they're going to lie in a unique plane, as long as they're not the same line. We talked about that before. If you have 2 lines that intersect, then 100%, as long as they're not the same line, if they're not coincident, then that's going to define a unique plane. But with 2 lines intersecting, that's 2 straight sides intersecting, that's also going to form a unique angle as well. Okay, the plane containing angle ABC is separated into 3 subsets by the angle. Points such as D are said to be in the interior of angle ABC. Points such as E are said to be on angle ABC. Points such as F are said to be in the exterior of ABC. So, okay, yeah, that's just some more terminology here. The point D is, you say that's in the interior of angle ABC. Point F is on the exterior, and point E is on the angle. So that's something to think about. That's kind of interesting. Because this might seem obvious, but if you think about it, it's not that obvious, because maybe you'd say point D is on the angle, right? It's like anything here, you're on the angle. Well, no, technically no. That's in the interior of the angle, or you could be on the exterior of the angle. If you're on one of the straight sides or the vertex, then you're on the angle. And another way to think about that is a ray like this extends out to infinity. So even if you go way out here, you have a point here, that point's on angle B. All right, with this description, it is possible to state the angle addition postulate, which is the counterpart of the segment addition postulate. So yeah, this is the segment addition postulate was if you've got a segment, AB, and then some point that's collinear with A and B, and so it means it's on, but between A and B, so it means it's on the segment, some point X. Then the length of AB is equal to the length of AX plus the length of XB. And so here we're going to see the parallel to this when it comes to angles. So it's going to be pretty simple. We've got, so point D is in the interior of an angle ABC, so it's in the interior. Then the measure of angle ABD plus the measure of angle DBC is equal to the measure of angle ABC. The measure of angle ABC is equal to the measure of angle ABD plus the measure of angle DBC. So, okay, we've got theta, alpha, and then the whole angle is, measure of angle ABC is equal to alpha plus theta. Okay? This is just a postulate. We're not going to officially prove this, but it's common sense enough to where we can make this based on the definitions and the other postulates we've used. This is kind of common sense you could think about. All right. Let's see. Table 1.4 angles. Angle 1 is, what are we doing here? Oh, okay, yeah, acute angle. If we took out the protractor, we would see this is 23 degrees. We could do that, actually. Why not? Yeah, you see it's 10, 20, right at around 23. Here's a right angle. Here's an obtuse angle, straight angle, reflex angle. And a reflex angle, we've talked about this before, but you could use a 360-degree protractor, or you could, extend that line, make a straight angle, and then just do like this. So you get this obtuse angle and then add 180 to that. So this is at what? A little bit less than 160, 158 or something. So 158 plus 180 is right around 337. So an arc is necessary in indicating a reflex angle, and it can be used to indicate a straight angle as well. So yeah, you have to have, if they had to put this arc here. Otherwise, we're going to assume that they're referring to the acute angle. So you have to have an arc to indicate a reflex angle, but you could also do that for a straight angle as well, since that can be ambiguous as well. But you can also do that for a straight angle, since that can be ambiguous. All right, use figure 1.48. That was, so I'll bring that over here, on page 29 to find. So the measure of angle ABC, if they're telling us measure of angle ABD is 27, and then DBC is 42. So 42 plus 27, 69 degrees. You're just adding, right? You just add these two. What is the measure of angle ABC if ABD is x and DBC is 2x minus 3? So ABD and DBC, you just add those two. X plus 2x minus 3. 3x minus 3. That's it. Okay, classifying pairs of angles. Many angle relationships involve exactly two angles, never more than two angles and never less than two angles. Yes, there's a lot of situations where what they're saying here, there's a lot of circumstances where you're just dealing with two angles. It's not always the case. You could be dealing with more than two sometimes, but there's a lot of scenarios where you're dealing with two angles. And so what we're going to do is we're going to come up with some classifications for pairs of angles. In figure 1.48, angle ABD and angle DBC are said to be adjacent angles. In this description, the term adjacent means that angles lie next to each other. In everyday life, one might say that the Subway sandwich shop is adjacent to the Baskin-Robbins ice cream shop. That means they share a common wall, is the way I would look at that. If they're in a complex. And that's the idea here. If you share a common side, then the angles are adjacent. So they're saying this angle here is adjacent to this angle here. Okay, but it's not just a common side, but it's also a common vertex. Okay, but in figure 1.48, angles ABC and ABD, ABC and ABD are not adjacent because they have interior points in common. Notice that the common side, ray BA, does not lie between angle ABC and angle ABD. Okay, so yeah, that's important to note that this angle and this angle are not adjacent. They share common interior points. So they don't share any interior points, but they share a common side and a common vertex. That's what adjacent means. They don't share any interior points. They're not like mixed in with one another. They're two distinct. They're two distinct separate angles, but they're going to have to share a common side and a common vertex. Okay, so definition. Here's an official definition for this. The angles are adjacent. Yeah, what is the official definition? They have a common vertex and a common side between them. So, okay, that is the definition. I thought I was talking more informally there, but that is actually the official definition. If you have two angles that share a common side and a common vertex, then they are adjacent. Now, what if you have the same angle? Here's angle ABC, but that's also angle GEF. Are those adjacent angles? Well, no. I would say no, because it says they have a common vertex. Okay, that checks out. A, B, C, and GEF have a common vertex. Okay, and a common side between them. Well, these don't have a common side. They have two common sides. The way this is stated is it's like one common side. So these have two common sides. It didn't say that. It didn't say at least one common side. It says a common side. So no. So you might think, okay, that means congruent angles aren't adjacent. And that would be incorrect, because remember that we're going to now recall the meaning of congruent. What was congruent? When two angles have the same measure. That was it. So you're allowed to, so you can have two adjacent angles that have the same measure. But when it comes to congruent, the key to this is that when it comes to congruence, you're allowed to do an imaginary shifting in space and see if they line up. That's okay. So what I was just talking about was not, when I said the same angle, that wasn't congruent angles. That was the same angle. They're already oriented on top of one another in space. They're not two distinct angles. All right, so that's a congruent angle. They have the same measure. That's it. And the reason is because you have this angle over here has a certain measure, and if you had this angle over here that has that same measure, to determine congruence, you could just reorient these and line them up, flip them, do whatever you want, and if they line up perfectly, they're congruent. Well, when it comes to a measure of an angle, that makes sense. Angles are they're simple enough to where their measure determines congruence. That's not always the case. We've talked about this before. Two triangles have the same measure. I guess you could say the same area. It doesn't mean they're congruent. But it works out that way with like line segments. If they have the same length, they're congruent. Two line segments. Same with angles. It just works out that way. Congruent angles must coincide when one is placed over the other. Do not consider the sides appear to have different lengths. Yeah, the sides of the lengths of the sides don't matter in the case of angles, because the side lengths. You might say, well, why is that? Because for the definition of an angle, the side lengths don't matter. They're talking about rays, right? For the official definition of angle, the sides are rays. Rays don't have a length. There's no length of a ray, just like there's no length of a line. So that tells you the side lengths don't matter when you're dealing with angles. Only the orientation of the sides. Yeah, remember that rays are infinite in length. In symbols, angle 1 is congruent to angle 2 if measure of angle 1 is equal to the measure of angle 2. In figure 1.49, as well as in later figures, similar markings indicate that the two angles are congruent. Okay, yeah, there's the symbol, the congruent symbol. That's the two figures of the angles as figures. But now measure means numbers, so you put the equal. But congruence is to indicate, it's like the parallel of equals, but with figures. And then, yeah, this we're going to see as we go through geometry, this marking here is a way of indicating that congruence of angles. Or you could do like, we'll see. Yeah, like just note this here. Note this marking here. Well, but you'll learn more about this as we go. All right. Given measure of angle 1 is congruent to angle 2. Measure of angle 1 is equal to 2x plus 15. Measure of angle 2 is equal to 3x minus 2. Find x. We'll just set these equal. Okay, subtract 2x from both sides. So you get x minus 2 is equal to 15. Add 2 to both sides. There we go. And then you could plug x back in and get angle 1 and angle 2, the measures. All right, definition. The bisector of an angle is the ray that separates the given angle into two congruent angles. So we've already talked about bisector, but we never officially defined it. So here's the official definition. The bisector of an angle, okay, it's a ray. It's a ray that separates the given angle into two congruent angles. Now, I want to point out here that they're using the term ray here, and the point of you don't let that bog you down to thinking that if I don't see a ray, there's no angle there. It doesn't work that way. But the term so does that mean the term ray is unnecessary here, or it's unnecessary the definition of an angle? No, it's very necessary to establish the constraints on what makes an angle. So yes, if this was, so we have three rays, if this was just a line segment in P, that's fine. The ray is telling, the purpose of ray in the definition is to tell you that the length of the line doesn't matter. That's why you want ray. So if the length of the line doesn't matter, then if it's a segment, that's completely fine. But if you didn't use ray here for the definition of angle, then that would imply, okay, well then it's the length matters, because line segments have a definite length, you see? So, okay. The bisector of an angle it's a ray that separates the given angle into two congruent angles. So, okay, you start off with angle MNQ, or angle N, and now you add a ray that's going to separate that angle into two equal angles. You see, there's that symbol. They use two lines this time. Indicates that. So like the idea is if you like these two are congruent with that. They put one line, and the two lines indicate that these two are congruent, but they're not congruent to the one line symbol. That's how you do that. Indicate congruence with angles. Okay, but now let's think about, could we interpret this as maybe they're talking about the obtuse or the reflex angles here? Well, that's not going to work. If you draw this line here, well then if you still interpreted it this way, you haven't separated. If you were initially referring to angle MNQ and you wanted to think about bisecting MNQ, well, this wouldn't do anything. You haven't separated MNQ at all. So this is separating the acute angle. Okay, and so if you drew a ray in this direction, then you're separating the acute angle to two separate angles. If those angles are congruent, then NP bisects, ray NP bisects angle MNQ. And we can think about that these are adjacent angles as well. MNP and PNQ are adjacent. So let's see. With P in the interior of angle MNQ, so that angle MNQ is congruent to angle PNQ, ray NP is said to bisect angle MNQ. Equivalently, ray NP is the bisector or angle bisector of angle MNQ. On the basis of figure 1.50, possible consequences of the definition of bisector of an angle are measure of angle MNP is equal to the measure of angle PNQ. Measure of angle MNQ is equal to 2 times the measure of angle PNQ. Yeah, there's different ways of looking at it. Just like we did with the length, the segment bisector. This is half of this. This is half of this. The full angle is twice times either one of those. All right, another definition. Two angles are complementary if the sum of their measures is 90 degrees. Each angle in the pair is known as the complement of the other angle. Okay, so this is a little bit confusing because, so if you might be thinking, well, I thought complementary angles had to be acute angles. So this seems to be suggesting that if you had, you can have negative angles depending, it's just like a coordinate system, right? It's like you can have negative velocities and lengths. So, okay, if you had minus 120 plus 30, so an angle of minus 120 degrees and an angle of 30 degrees, those two are complementary. Well, no, right now we're still talking from the perspective of the measure of an angle is a positive number. We haven't thought about the idea of a negative angle, which is just like a construct that we use to, it's like a negative velocity. Is anything really moving with a negative velocity, literally? Well, no, that doesn't make any sense. But yeah, you can have negative velocities. It's like, if based on the problem, one car is traveling in the other direction of another car. That's the way you indicate that one's going in one direction, one's going the opposite direction. But right now, we're looking at this from the perspective of there's no negative lengths and there's no negative angles. We're just a pure measurement of an angle or a length. And so in that case, they don't need to state that the angles need to be acute. By consequence of this definition, you can't have a complementary angle that's not acute. Two complementary angles that's not acute. Because how are you going to, if there's no negative angles, how are you going to have any angles that sum to 90 that aren't acute angles? Okay? So two complementary angles are going to be, they're two angles that sum to 90. But we're not talking about, with the definition of complementary, we're not talking about negative angles. It's just 0 to 360. And for that matter, we're not even talking about angles that you can have a 390 degree angle. Again, we learned that in trigonometry. You can do that, but from the pure perspective of we're just looking at measurements in space right now, there's no 390 degree angle. It's one rotation. That's it. Okay. Angles with measures of 37 degrees and 53 degrees are complementary. The 37 degree angle is the complement of the 53 degree angle, or vice versa. The two angles are complements. If the measures of two angles are x and y, and it is known that x plus y is equal to 90, then these two angles are complementary. Okay. Now, there's also supplementary angles, means that the sum of the measures is 180 degrees. Each angle in the pair is known as the supplement of the other angle. So you can think about this in that this is going to be the two supplementary angles are going to be, so you can have the vast majority of the time, well, I don't want to say that, but there's a special case where you have two right angles. Two right angles are supplementary. Other than that case, if you have two supplementary angles, you're going to have one's going to have to be obtuse and the other is going to have to be acute. Because you can't have two acute angles because then it's not going to sum to 180. You can't have two obtuse angles because then their sum's going to be greater than 180. All right. Given that the measure of angle 1 is 29 degrees, find the complement of angle 1 and the supplement of angle 1. So 90 minus 29 is what? So 90 minus 30 is 60, then add 1 to that, so 61 degrees. What about the supplement? What is 180 minus 29? 180 minus 30 is 150, so 151. All right, if angle P and angle Q are complementary, and this is just with variables, we're going to work a bunch of examples. All this is really simple. If you clearly understand the definition of complementary and supplementary, it's just algebra. They tell us these two angles are complementary, and so you have one is x over 2, one is x over 3. Well, that means you can add these two and set them equal to 90, and then solve for x. So it's really just comes down to, after you understand that, well, here's a linear equation in one variable from algebra. When two straight lines intersect, the pairs of non-adjacent angles in opposite positions are known as vertical angles. Okay, so let's read this again. Vertical angles are important. When two straight lines intersect, here's two straight lines, the pairs of non-adjacent angles in opposite positions. So what are they saying here? The pairs of non-adjacent angles. So if you have two lines that are intersecting, you're naturally going to create some adjacent angles as a consequence. 100%. Because you're going to have on one, depending on what line you're looking at, let's say we're looking at saying line M intersects line L. From the perspective of line L, on one side of line L, you're going to have two angles that share a common side. And that's going to be the side created by the intersecting line M. And it's the same idea on the other side. But you could also use that, what I just stated, you could say that from the perspective of line M. So you're going to have these adjacent angles that are going to be created. It's specifically 4. Two intersecting lines, you're going to have these 4. Well, not all of them are adjacent. It's like you have two adjacent angles and then two other adjacent angles. Because why aren't they all adjacent? Well, because, okay, is angle 6 adjacent to angle 5? Well, no, they don't share a common side. They have a common vertex, but they don't share a common side. Angle 6 is adjacent to angle 8. Angle 5 is adjacent to angle 7. So, again, let's think about this. You have two lines that intersect. And this is universal for no matter what the case. If you have two lines that intersect, no matter how they're oriented in 3D space, we know that two intersecting lines are going to form a plane, a unique plane. So you're going to, with that, you can view these intersecting lines from a plane. If you have any kind of weird 3D space, lines oriented in 3D space, okay, one's coming up here, one's going, who knows? But they intersect, okay? They intersect. Then that's going to make a unique plane. So you can imagine taking that, like you do in like a solid modeling software or whatever, you kind of click and it brings this into view straight in front of you and it kind of puts it on a plane like this. Okay? When you can do that, and then you'll always, if the lines are intersecting, this is 100% every time, you can break it down this way. You're going to have a pair of adjacent angles and two pairs of adjacent angles, of different adjacent angles. But it's kind of like, but it depends on which perspective you're looking at it from. Like from the perspective of line M, you got adjacent angles 5 and 8, and adjacent angles 6 and 7. From the perspective of line, well, no, that doesn't matter about perspective. Here we can see 7 and 5 are adjacent, 8 and 6 are adjacent. But then, it does. The perspective does matter because also 5 and 8 are adjacent and 6 and 7 are adjacent, but they're not all adjacent. So it's not, this is kind of tricky. It's not just that, okay, 5 and 7 are adjacent and 8 and 6 are adjacent, and that's it. No, also 5 and 8 are adjacent and 7 and 6 are adjacent. But 5 and 6 are not adjacent. 7 and 8 are not adjacent. And so they get their own term. They're called, those are the vertical angles. They're non-adjacent and on opposite sides of the vertex. So, really, I think you could just say here non-adjacent. If they're not, if you have with respect to intersecting lines, the non-adjacent angles are the vertical angles, and that's it. You don't need to say opposite positions, because that implies that we can find some non-adjacent angles that are they're not in opposite positions. They're in like a kind of a different position than opposite, but that's not the case. You're either going to be a non-adjacent angle or an adjacent angle. That's it. And so the non-adjacent angles at an intersection of two lines, those are the vertical angles. All right. So in figure 1.51, angle 5 and angle 6 are vertical angles, as angle 7 and 8. In addition, angle 5 and angle 7 can be described as adjacent and supplementary angles, as can angles 5 and angle 8. Yeah. So these are vertical. We know what the vertical angles are, but you can see angles 5 and angle 7 are supplementary. And this is every time, no matter what. It could be a perpendicular intersection to where angles 5 and angle 7 are equal. That means it's 9 degrees, but that's not the case every time. But for any intersecting lines, no matter what, the adjacent angles are going to be supplementary. Angles 5 and angle 7 are supplementary. Angles 6 and angle 8 are supplementary. Angles 5 and angle 8 are supplementary, and so are 6 and 7. Okay, so if you knew that angle 7 was 30 degrees, you could solve for angle 5, taking 180 minus 30. All right, now it is true in general that vertical angles are congruent, and we will prove this in example 3 of the 2 sections from now. Okay, that's cool. Vertical angles are going to be congruent. That's a universal fact, and we're going to prove it later. So vertical angles are congruent. Recall the addition and subtraction properties of equality. So if A is equal to B and C is equal to D, then A plus or minus C is equal to B plus or minus D. These principles can be used. Yeah, we talked about this before. The idea of how can you add 2 equations. So go check that out. And we talk about that in the algebra playlist. The idea of how can you add 2 equations. What does that mean? It's like I could add 5 to both sides of this equation. I'll add 5 to the right side, 5 plus 7, but then I'll add x plus y to the left side. Or I could add 7 to both sides of the top equation. Okay, so that's solving a system of 2 equations and 2 unknowns. They're just reminding you how to do that. When each term in an equation is multiplied by the same non-zero number, the solutions of the equation are not changed. Yeah, we know with equations you can add the same thing to both sides, subtract the same thing to both sides, multiply or divide the same things to both sides, except you can't divide by 0, and you don't change the equation. Okay, so yeah, they're just reviewing that. So they're reviewing that because, okay, look at this problem. In figure 1.51 on page 32, if L and M intersect so here's figure 1.51. So here's the measures of angle 5, 8, and 6. So now they say find X and Y. So let me actually bring this right here. So, okay, if angle 5 is 2x plus 2y and angle 6 is 4x minus 2y, we know that those two are equal. So we could start there. We could set those 2 equations equal to one another. Let's do that. Yeah, okay, so 2x plus 2y is equal to 4x minus 2y. So you add 2y to both sides and subtract. Well, let's actually subtract 2x from both sides. So you have 2x and subtract 2y from both sides minus 4y is equal to 0. Okay, now we can divide both sides by 2 and get x minus 2y is equal to 0. So we got, there's an equation. Hello. X minus 2y is equal to 0. Okay, now what else? Well, we've got 5 and 8, or 8 and 6, which are both of those are supplementary. There's 2 supplementary pairs, so we can add angle 5 to angle 8 and set that equal to 180, and they'll get another equation, and then you solve 2 equations and 2 unknowns. So we're going to work a bunch of examples. just like this. But the key is understanding this relation of angles between intersecting lines, the 4 angles that are created. All right, constructions with angles. So we did constructions with line segments. This is just when we're going to use like a straight edge and a compass to do some constructions. And this is, we have computers today, but this is still valuable to get back to the roots of geometry. Even computers are designed still with these fundamental principles in as the backbone. So it's good to work with a compass and a straight edge, and that just gives you a good sense of the fundamental principles of geometry. So, all right, previously we did constructions with line segments. Now consider 2 constructions that involve angle concepts. In section 3.4, it will become clear why these methods are valid. However, intuition suggests that the techniques are appropriate. Okay. So, to construct an angle congruent to a given angle. So yeah, the main idea of the construction that we did with the line segment in section 1.2 was that you could, if you fixed the radius on your compass. So what we just to remind you, what we did was we had like a line or a line segment or whatever, but then we put our ruler and measured like 5 inches or something, or 2 inches, and marked that off on the line segment. Then we set our compass, we fixed the radius at 5 inches using this. So you measured off like 5 inches, marked it off, then put the center point, fixed the center point of the compass here, and then adjusted the radius where the pencil was to here, and then fix that on the compass. Then with that, you can take your compass wherever you want, and just you can draw. You can make line segments you can make congruent line segments in any orientation you want, because all you do is just you go and you draw a little arc, mark off the center point. You can just draw a line anywhere on that arc, and that's congruent to this line segment, no matter what the orientation is. That was the idea of the constructions with line segments. So now here we've got, so given angle RST, all right, we're going to construct ray PQ as one side to where angle NPQ is congruent to angle RST. So to do this, they go to, so in figure 1.52b, with a compass, mark an arc to intersect both sides of angle RST at points G and H. So, okay, they take this angle and then make an arc. All right, now without changing the radius, mark an arc to intersect ray PQ at K and the would-be second side of angle NPQ. So now you draw ray PQ, and then you draw an arc with that same radius to where it intersects PQ at K, and then, just kind of estimate the would-be side of, you're trying to make a congruent angle. But so just draw it long enough to where you for sure it definitely it goes through what would be the side of the opposite end of this NPQ congruent angle. Now mark an arc to measure the distance from G to H. Okay, so you come here and you make an arc. So you would adjust the radius of the compass here. Now using that same radius, mark an arc with going from K to here. And where they intersect is where you're going to draw where those 2 arcs intersect is where you're going to draw the ray PN. See, that's pretty cool. And so then you have a congruent angle. All right. So that was constructing a congruent angle, but now they're saying just as a line segment can be bisected, so can an angle. This takes us to a 4th construction. So we worked a construction before where it was like we got the midpoint of a line segment we just extended. We had a line segment. We made the radius of the compass fixed at some length that was definitely greater than the midpoint, and then fixed it in. Then we drew an arc like this. Then we had the center fixed here. Then we fixed the center here and drew another arc like this. And then it was these 2 lines were like perfectly vertical, and that mapped out the midpoint. Okay, so here to construct a bisector of an angle, so given angle PRT in figure 1.53a, so okay, here, so construct ray RS so that angle PRS is congruent to angle SRT. So we want to construct this ray RS, so PRS is congruent to SRT. So, okay, in figure 1.53b, using a compass, mark an arc to intersect the sides of angle PRT at points M and N. So this is just arbitrary, just pick a radius. And then now with M and N as centers, mark off two arcs with equal radii to intersect at point S in the interior of angle PRT as shown. Now draw ray RS, the desired angle bisector. So, okay, what they did here was that they then, so, okay, at this step, they put the center of the compass at M and N, picked any radius, didn't matter, and then drew two separate arcs, and where they intersect, that's what you're going to draw the RS through, and then that's going to create that means it's going to bisect angle R. Pretty cool. Reasoning from the definition of an angle bisector, the angle addition postulate, and the protractor postulate, we can justify the following theorem. All right, there's one and only one bisector for a given angle. Yeah, this is the same idea as the midpoint, the uniqueness of the midpoint. There's only one midpoint, and in this, it's the same reasoning in that there's only one length of something. You can't have multiple. If there's one length of something, then there's going to be only one midpoint. Like if there's only one length of a line segment, there's only going to be one midpoint. Same idea with an angle. So the bisector of an angle is unique, and we're going to prove this more officially later.